Hey guys, welcome to the second half of the video. So at the end of the last video, we did a problem that involved using adding the two vectors together and the I and the J. And so what I'm going to do is I'm going to apply it to this very first problem that we did. So as I said in the other video, I made a mistake on this value. So I fixed it. I fixed all the values here, so they're good now. And the way I did that was doing it the other way, and I caught my mistake. So sometimes it's nice to be able to do something two ways so you can kind of catch silly mistakes that you make. Okay, so the first thing I'm going to do is I'm going to alter this picture. So this 54 degrees is going to be up here. So it's going to be, I'm just like shifting it in this direction. And so I'll explain that here in just a second. Okay, so I'm going to go back up to the picture, but I want to kind of give you a head start on what I did. So I made that 54 Newton force at a 0-degree angle. And then I made the 42 Newton force at a 98-degree angle. And this is why I did this. Because, so here are the two forces here. So the angle between the forces is 98 degrees. So and let's go back up to the picture. I'm going to try to erase all this craziness in here. So I just shifted this up here, and so all of this stuff is moved over. Okay, so that this line right here is a resultant vector, and I do not know what that theta is. So I'm going to need to find that out here in a minute. As we learned in the last problem, the resultant vector is the sum of the two forces. So I'm just going to apply that. Notice that the direction for this is, for this 54 is 0 degrees, and the direction for the 42 is going to be 98 degrees. So that's what I'm going to use in my formula that you're going to see. Okay, so this is my formula. So I'm just adding the two vectors together. So if you'll notice, that's what I did there. Now, as we did before, we're going to group all the I's together and all the J's together. So you don't have to do it, especially on this one, because I want to show you something. This is what's nice about this is, sorry, not 90 degrees, 0 degrees. Cosine is 1 and sine is 0. So right here, my answer is 1. Plus 42 cosine of 98. And this is going to be 0. So this just cancels out, and I have 42 sine of 98j. So what I'm going to do is I'm going to get this value and this value. Sorry, I forgot to multiply this times the 54. So this is 54 instead of 1. Okay, so I end up getting 48.15i plus 41.59j, which is the same thing as this. So now if I have that, I can easily do the magnitude. So I'm going to do this squared plus this squared equals the magnitude squared. So let's go ahead and do that. And I ended up getting 63.63 newtons. So let's go up and see how that compares. Oh, look at that. The decimals will kind of be off a little bit. Like I got right here, when I did it the other way, I got 0.625, but it's going to give you what you need. Okay, so now let's figure out what that theta is. So I have these 2 points right here, and so they're both positive. So I know that they're both in, that point vector, or whatever you want to call it, is going to be in that first quadrant. So it's going to look like that. So we're trying to find that theta there. So I'm just going to, even though I have the magnitude, I can plug that in. I'm just going to use tangent inverse of, and see what I get there. So I ended up getting 40.82. And so that is just this little piece right here, 40.82. Okay, so let's see if we found that piece up here. Oh, look right there. So what I'm going to do is find this piece right here. So I'm going to take 98 minus 40.82, and that will give me this other piece. And I end up getting 49.18. Sorry, I subtracted from 90, 57.18. And let's see, right there. Okay. So everything is super consistent with this other problem, but I still haven't answered the problem. So then find the angle between the equilibrium and the 42 Newton force. We're going to have to visualize what that means because our picture looks different than it did up here. So if this is that vector that we found, remember the equilibrium vector is going back this way. So if we found that this angle right here is 57.18, then we just need to find this angle. So I'm just going to take 180 minus 57.18, and I end up getting 122.82 degrees. And let's see. And that is the same thing that we found before. So it's just a little bit different. On the homework assignment, it's going to show you both different, or the both ways. So you can kind of practice using both ways. Okay, so the last thing I want to talk about is way down here. When we have equilibrium. So I always kind of think about this as me hanging on the monkey bars. And so think about that. Where do you feel the pain? So when you are hanging on the monkey bars, don't you feel that in your arms right there? I do. I definitely do. So what it is it's this force going this way and this force going this way, and you're holding yourself on those bars to counteract this force that's going down. And it's holding you in one place. And so that is what's going on here. So when we have all these forces together, because you are still in one place, you're not going this way, you're not going this way, you're not going down, those forces are always going to add up to zero. So this is a perfect example of what this might look like. So you have these forces working together, they give you the angles. A lot of times they'll give you the weight of this. This is going to be a negative weight. So that's going to be like pulling you down. So that's going to be a negative weight. Okay, so let's go ahead and read through this problem. We have a weight of 800 pounds that's suspended from two cables. So let's pretend that this is 800 pounds. On the left, the horizontal angle is 35 degrees, and on the right, the horizontal is 50 degrees. So instead of these two, we're going to put in 35 and 50. So go ahead and make your picture. Okay, so your picture is going to look like this. And when you're doing this, I want you to think about the problem that we did before with these two angles that we were dealing with, because it's not going to be what you think. So when we have this force, we're not using necessarily these two. What we're going to do is we're going to do the force here and then the force here. Well, because these are parallel, this force is 50 degrees, so that matches. But this force right here is 50 degrees plus this angle. So we're going to have to find the angle. So I'm going to take 35 plus 50 and then subtract that from 180, and I get that the missing angle in the triangle is 95 degrees. So I'm going to take 95 plus 50, and I get, sorry, put it wrong, 145. So this angle right here, that second force, that's going to be 145 degrees. So we're dealing with 145 degrees and 50 for those two angle measurements. So now we're going to add all the forces together, and you have three forces acting together. So you have, like I said, the one force that's a 50 degrees, the other force that's 145 degrees, but then you have this force working down, and notice that it's not it's not anywhere horizontal, so it is straight down. So this is going to be a negative 800 pound force, but because it's straight down, we're going to call that J. So remember, the I is the horizontal unit and the J is a vertical unit. So because it is up and down, you're going to see that show up in our formula as J. So I'm going to go ahead and add those three forces together, and don't forget we're going to set them equal to 0. Okay, so I've added my three components together and we are going to set it equal to 0. Okay, so just like I did before, right now I have them separated into the three forces, but I don't want to do that. I want to group them in terms of I and J. And so let's do that next. Okay, so I think I have them all grouped. And so what I'm going to do is I'm going to just find these values, clean them up, find these values, and just kind of clean it up a little bit. So we're still going to have like the F1 and F2 and all that yuckiness. But what I'm trying to do is turn it into like an IJ vector. So that's kind of where we're headed. So go ahead and clean it up a little bit. Okay, so this is our yucky IJ vector. And so I try to do it in different colors to signify the I and the J. So this is I and this is J. It just looks yucky however I do it. Okay, so for the next thing, notice that if we look at it like this, like it's got to be set equal to 0. This is equal to 0 and this is equal to 0. So I'm going to split those two things up. Okay, so I have these kind of set up. So what I'm going to do is I'm going to take this and just solve for like, I'm going to just call it, I'm going to solve for F1. So, and it doesn't matter. You can solve for F1 or F2. It doesn't matter. I'm going to move over that. So I have 0.819 F2, and then I'm just going to divide by the 0.643. So this is definitely like a calculator thing. So force 1 equals 1.27, let's call it 74 F2. So this is going to be like systems of equations. So I'm going to take the F2 or F1 and I'm going to plug it in there. So what we're doing is we're getting it all into like the F2 group. So I'm going to say, I'm going to erase this. So 0.766 times F1 plus 0.574 F2 minus 800 equals 0. So I'm just going to really clean this up. So I ended up with F2 equals 516.24 pounds. I did not round, but if you round to like 1.55, you'll get 516.13. So it depends, like there's some wiggle room there. So once I have F2, then I can plug that in here and find F1. So go ahead and do that. Okay, so I ended up getting for the first force 657.69 pounds. And again, like this differs a little bit. So if you can like round up to 658, you probably did your numbers correctly. It's just depending on like where you rounded and stuff. And so we found the tension of the two cables. So this is that first force and that's that second force, and that is it.